Hello, PreCalc. This is the 17th or the 18th or the 19th. So we have a choice of watching this on Friday after class, Saturday, the 19th, or the 20th. So we have Monday off. So we have several choices, but you need to watch this video before Tuesday's class. We'll be looking more into our study of exponential functions. So we're headed toward logarithms. Won't get there today. So if you have an inherent fear of logarithms, you can rest assured and breathe easily. Recall that an exponential is of the form y equals some number to the x. That's an example of an exponential. And we learned that this, for an example, y equals 3 to the x. This is the base number, and that's the exponent. And we saw how these exponentials can take on negative signs various places, like there, or in front, or both. And we were graphing each of those. Exponentials can also take on whole expressions and be like this. So instead of just raised to the x, it can have here a whole expression in x. And we can add numbers to the whole expression. We won't get into that, but I want you to be aware that that can happen. Tonight, which I promised to do, is a very special base number, a very special exponential function. So the base that is very special is y equals e to the x. And e is a number, and Jacob Bernoulli actually, I think, discovered it. He named it. It's like 2.718281828. You think it's going to keep going like that, but then it doesn't. It goes 459045235360 and it continues. It never ends and it never repeats, just like pi. So I think we should have an E day on 2/7. So that's February 7th. Ah, we missed it. All right. So next year, let's have an E day. Jacob Bernoulli discovered it, but a man who worked with it, Euler, that's how you say it, it became Euler's number because of his work with it, and thus the name E. So it's quite an honor. And it's probably the most important number in mathematics. And it's fairly new on the scene. All this took place in the early 1600s, which is fairly new compared to like pi. This number, I say, is so important because it pops up when we study population growth or decline. It pops up when we watch the growth or death of viruses, bacteria growth. It pops up in finance when we see our money grow. It pops up in statistics every day. In stat class, we look at the normal bell-shaped curve, and its formula has E in it. It's basic to radioactive decay, chemicals that behave that way, elements that decay radioactively are obeying a formula with E in it, and it goes on and on and on. It's even in The Simpsons. I think if I'm right, if I remember right, I haven't seen many Simpsons, but don't care to. Sorry. But I think it says this version of The Simpson will be brought to you by the number something and the letter something. And one time it says this version or this episode of The Simpsons is presented to you by the letter A and the number E. And they say that's not a mistake. We're talking about the number E. So it's everywhere. E is the epitome of growth. So let's look at some growth situations like money. So I'm just going to do some theory here and we'll get back to the math, I promise. So if we have some money and say we start with a certain amount of money, at the end of the next term, let's say it's a year, the money doubles. And say after 3 years, it doubles again. So at the end of each year, it's going to double. So the 4 becomes an 8. Well, that's an example of exponential growth. Y equals 2 to the x, like that. And we talked about that already. So what about a different kind of growth? And this growth isn't very natural. It's sort of like there's one amount of money, and at the end of 2 years, pop, it turns into double. And then at the end of the next year, it pops, and it turns into 4, and it pops. It's like it suddenly appears. So that's sort of unusual type of growth. So let's look at something that's more normal growth, and that would be a more smooth and steady growth. This is almost like stairs, like suddenly it pops up. But I don't like cell growth. I'm going to talk about cell growth. And that is, suppose there's one cell, like that. And then the cell begins to grow. So we see growth starting out of the cell. And then that growth grows bigger until it is mature. Let me make this one like bigger than this, but not quite that big. So it grows, and then finally it doubles itself. That's a more natural sort of growth, like that. But that isn't even where I want to go, because where this falls short is now this cell will start to grow, and then this cell will grow. But until this day, only this cell will be growing, because this cell has to mature totally before it starts its growth. So I want something that's even better, so to speak, than that. So let's look at an example here where we have, say, money, and this money is allowed to grow. So in the beginning it sort of looks like the cell growth, but this, even though that a bit of money is small, it's allowed to grow. So then we have this growing, this getting bigger, but at the same time this one has its own little bit of growth. So then it's kind of hard to draw, but then we would have this getting bigger, then this getting bigger, and then this has its own growth. So very difficult to draw. Let's say these are the gray ones, and the gray ones are growing, so those are the white ones, and then the white ones are growing, those are the spotted ones, and then the striped ones are the growth of that. So then we would continue, and the gray ones The white one is totally grown now. And then we have the spotted one that's pretty big, almost grown full size. This has growth, the striped one. And then the striped one has growth, which I don't know what color to put that. I'll make it black. All right. All right. That kind of growth follows a different kind of curve, very special. And that is y equals e to the x. And you think, when I think of e, since I can't contain this big long number, I just think of 2.7, which is approaching 3. So something around between 2 and 3. This is what e to the x gives us. It's growth of growth. And it's a very interesting way to observe what E looks like or what it does. And it is very naturally found in money situations where all of our money is compounded continuously. So any money we make is also growing money. And that's the best comparison I can come up with. All right, keeping that in mind, this E does show up everywhere. We're just going to explore one place where it shows up for the rest of our evening. And that is in compound and continuous interest growth. So compound interest doesn't really have E in it, but we'll go ahead and cover it and give you exercises in it. And then we'll upgrade it to compound interest, which is taking continually. It's called continuous growth. So compound interest and continuous interest. All right, so we know when we put money in the bank that it will grow extra money by a certain percentage rate so many times per year. So we know that it will work like this. Say the first year I have an amount of money, and that money is going to be P. Then the second year, because of interest rates, I'm going to get P back, but P times R. The interest rate will be applied to the principal, and we will get what we put in to start with. So it'll grow by this amount. So I can rewrite that factoring out the P, 1 plus R. And then the third year, it's not really, this is really at the beginning. So this is the end of, let me call this A sub 0, A sub 1, A sub 2. So this is really the end of 2 years. We're going to take this amount and add to it P times 1 plus R times R. Now we can factor out this because each term has that, so it equals P times 1 plus R. I pulled that out of here, so it leaves a 1, and I pulled it out of here and it leaves an R. But that's the same as that, so I can call it P times 1 plus R squared. So a little algebra shows us that in the end of the first year we have P times 1 plus R, and the end of the second year we had P times 1 plus R squared. So, seeing a pattern, the end of the third year is P times 1 plus R cubed, and so on, till we get any time, the amount at any time equals P times 1 plus R to the T. Now, this changes slightly, and I won't show you all the ins and outs of how it gets to that, but this is when we compound, we calculate our interest once a year. That's like this pop goes the money. But here, normally, we do not compound our money. That means calculate our interest and add it once a year. It could be quarterly, that would be 4 times a year, or it could be monthly, 12 times a year. So we compound more than 1 time per year, and we'll say that the number of times we compound, so number of times compounded or calculated, we'll change this slightly to this 1 plus r divided by n to the n times t. And that can be explained, but I'm going to just give that to you for my purposes. That will work. So let's use this. This is compound interest formula. And let's do a problem. So I'll keep that in the screen and come over here. Say I have $12,000. And I'm going to put it in a 9% interest-bearing account, which is unheard of. Now they're about 0.1, something like that. I'm going to have it compounded quarterly, and I'm going to keep it in there for 5 years. So how much will I have? So I'm going to take this formula and put in the numbers. The amount at time 5 years, is going to be the principal I started with, 12,000, times 1 plus the rate of interest, which is in decimals, 0.09, divided by the number of times it's compounded in a year, so quarterly would be 4, raised to the 4 times 5 is the number of years, 5 years. All right, so I'm going to calculate that, and when I do, I got $18,000, $18,726.11. All right, now I'm going to do the same calculation, but I'm going to change this to monthly. We're going to calculate it monthly. So let me flip over, find some more working space. So I had the amount of $18,726.11. So I'm going to do the same formula. A equals P, 1 plus R over N to the Rn. I'm sorry, to the NT. And I'm going to this time say, what's the amount in 5 years again? Where I start with the principal. $12,000, 1 plus the rate of interest is still 9, but I'm going to compound it 12 times a year, 12 times 5. You'll note that I get more money, but not a whole lot more money. It turns out it comes out to $18,788, $18,788.17. So there is some more, but for 5 years it's not a big difference. We went from 26 to 88, so a little more than $60. All right, now there is a scenario where we would compound it more than 4 times a year, more than 12 times a year, more than 365 times a year, but we actually compound it continuously. And that was like the little growth chart I showed where any growth had more growth. So it's continuously compounded. And it can be shown mathematically that the formula for that, and that's why I put it in this lesson, has E in it. It's the principal times E. Who would have thought E would pop up in the middle of a finance equation? E to the RT. So I'm going to say A equals 12,000, the principal. E is just E. It's the number almost 3. R is the rate of interest, was still 0.09, and the time is still 5 years. So the amount comes out to be $18,819.75. So more, but not a whole lot more, but it is more. So if you get the choice, compound continuously, or the greatest number of times per year that your financial institution will allow. All right, we'll be calculating some of these money equations and also using E in other scenarios. That's it for tonight. Over and out.